So we're moving on to ethers and epoxides. Ethers, as a reminder, have oxygen in them. They can't hydrogen bond to other ethers, but they could to water, which means that these together as just ether would be capable of dipole-dipole interactions. When we're trying to name ethers, there's kind of two different naming conventions. The first is if one is symmetrical, which is pretty common, honestly. That would just be a di and then the substituent name. So there's 3 carbons there, so that becomes dipropyl ether. When they are asymmetrical, you need to have the longest of those chains as the parent chain. And then the other smaller chain is combined with oxygen as a substituent. It's instead of having a propyl group, for example, you'd have a propoxy group. So we just sort of take off that YL and add oxy at the end, okay? So, for example, this first one, the methoxybutane, this is your longest chain. We've got 4 carbons there, and then this becomes the substituent of a methoxy because there's 1 carbon, oxygen. Here we have propoxybenzene. So benzene has 6 carbons. It's the biggest thing that we have there, and this becomes the propoxy. And then we have 2-ethoxypentane. Now I did this on purpose because just to show you that the longest chain is here. You can have these ethers coming off the middle of that longest chain as well. So this would be the first, second carbon, 3, 4, 5. Oh, I drew in an extra 6. That should be 6. So sorry about that. That should be hexane. So this would be 2-ethoxyhexane. Sorry about that. Okay, so now we need to know how to synthesize these guys. Well, what we've already seen is that you can make this with an acid and an alcohol. So if you recall, this is very similar, to the mechanism that we've seen with acids and water to make an alcohol itself. So if we have an alkene, the electrons would go to the hydrogen. We end up having a base that's a leaving group. Our alcohol moves in there to that that cationic position. A base comes and removes that hydrogen, and that's basically you're getting an OR there instead of an OH, like you would recall with water, right? So if we were to add water, it'd just be an OH at the most substituted position. Why is it the most substituted position? Well, we need to have that carbocation the most stable location possible. Acid catalyzed dehydration of symmetrical ethers. So this is how symmetrical ethers are made. You just start with an alcohol and you add acid. So now this is a thing that can happen though if you leave alcohol around and it gets a little bit acidic for whatever reason, some type of contamination that occurs, you can end up making ethers. So this is an equilibrium, and that does sort of mean that we've got to make that happen or not, depending on what you're looking at, but yeah, this can happen. So we have a alcohol site right here that will come in attached to the hydrogen, whatever source that is, so any type of acid will work here. The electrons from another alcohol will come and kick that out, so it's SN2 type of mechanism if it's a primary. And then, excuse me, the alcohol ends up removing the hydrogen again, giving you the ether. That also means, though, that ethers can continually break down from where they are ethers into alcohols. So also something to be aware of. In Williamson ester synthesis, we are going to do this in basic conditions instead. So we're going to use an alcohol with NaH. So remember that's Na plus H minus. That's like a hydride. And then we complete that with like a methyl or an R group with a X of some sort. So this is a different example in this mechanism. So just making sure that you're aware of that, okay? So I gave one example here and another example down here because I'm using a different alkyl halide on purpose, okay? So the methyl group that's right here is this guy. So CH3 is right there, okay? So the first thing that happens is with NaH, the hydrogen's removed. That is going to make an H2 gas. It literally just bubbles out. It's great and easy. That gives you a really good nucleophile to kick out the chlorine here in this case, or whatever that halogen is, in alkyl halides. Now, in order to be SN2 step, you have to have either a primary or secondary alkyl halide there, okay? So that's how you end up making asymmetric ethers. So you can make both symmetric and asymmetric ethers. And finally, just like we can make an alcohol with alkoxymercuration, we can do that with an alcohol as well to make an ether. So here we have an alkene double bond, and using HgOAc in our alcohol, followed by NaBH4, instead of getting an OH there at the most substituted position, you get the Markovnikov products with the ether. And the advantage here again is just like we have seen with alcohols, is that there's no rearrangement. Okay. How can we use ethers in synthesis? Well, there's some things that we can definitely do. Let's say if we have acidic cleavage of some sort that is going on, we can take an ether, and if we're exposing that to an acid, remember we said that we could go back and forth with making those, but also making sure that there's heat present. That's going to make what's driving this equilibrium type of thing more to a breakdown of that ether rather than a building of that ether. So excess, whatever HX is, we're going to get the R groups one at a time. So here we have one that's attached to our halide from here. So HCl would be whatever R group you have with Cl, and another reaction of that with your alcohol there is going to give you the same type of thing with your other R group. So if it's a symmetrical ether, then you get two of these, which is way easier to deal with than having an unsymmetrical ether and trying to deal with this, but that can happen too. So I made this example so that it is different. We've, on each side it's asymmetrical. We've got ether on one, or an ethyl on one side, and we've got a methyl on the other. But here's what happens is that first the electrons go and grab that hydrogen there. Let me see if I can get a highlighter here. There you go. Electrons go back to the bromine. That bromine then kicks this entire group out. Okay, so you end up making your first alkyl halide. Then, in the presence of more HBr, these electrons will come and grab that hydrogen, which then repeats the process again. So you get this. So you get both products. If you were just writing this reaction out, it would be like you start with R1. Well, here, let me give you some specifics here. If you start with this and this with HBr, you should end up with that plus that, okay? So that's what you would get in this case. Next, moving on to epoxides. Epoxides can be confusing when it comes to how to name them. And part of the reason why is that since they have a triangle in the middle with an oxygen, some things work in different ways. There are two options for how we've sort of named these, and I've tried to keep these color-coded here for you so that you can see what those differences are. So the first option, we consider oxygen is the substituent. And we list where the number of the carbon in the longest chain, where the oxygen resides. And in this case, we do both of them. and that's going to give us an epoxy as a substituent. Okay, so I'm going to go through that example first with all 4 of the ones that I put below for you as examples. So if we consider 1, 2, 3, 4 carbons here, that would be a butane. And we would put in front of that 2,3 epoxy butane, because that is what's going to give you that name. Here, on the other hand, the longest chain would be 1, 2, 3. Okay, this would be 2-methyl 1,2-epoxy propane. In other words, this 1, 2, between the 1 and the 2 is where you're going to end up with that epoxy. It takes higher priority than just the methyl group, right? So if that's the longest chain, that would be the substituent coming off of there. We can do this with rings too. This would be 1,2-epoxy cyclopentane. Note that you cannot name that in the other convention. And finally, we have a longer chain here. So we have 1, 2, 3, 4, 5. So again, your epoxy gets the lowest possible number. So the numbering starts from over here as to give the 2 on the epoxy being the lowest number versus the 2 going to the substituent here. That gets the lowest number. So 4-methyl 2,3 epoxy pentane is how we're going to name that one. Okay, so now let me erase that and let's go back to where we were and think about the other way to name these guys. So option 2 is to list the substituents that exist on the oxirane ring, and the oxirane ring is the epoxide. And in this case, the oxygen is number 1 of that oxirane ring. You can have 2 and 3 be either on the left or the right, doesn't matter, those are the same thing, but that's how we name these. So looking at the second name, the green one. So in this case, the oxirane would be 1, 2, 3. This is a methyl substituent, and this is a methyl substituent. So we have both on the 2 and the 3, dimethyl oxirane. That's an R. My combined cursive and print, it gets a little bit confusing sometimes. Sorry about that. Okay, this would be, see, that's a mistake. This would be 2,2-dimethyl oxirane. Why? Because oxygen's number 1. So there we go. That would be 2,2-dimethyl oxirane. Here, we cannot name a double ring in this capacity. So we're not going to do that. We're not going to try to do that. Okay, and then last but not least here, we've got 1, 2 goes over here. Why? Because it's longer. And 3 goes over here. Actually, I don't think it's because it's longer. It's because it starts with an I, and I comes first in the alphabet. So this becomes 2-isopropyl 3-methyl oxirane. Personally, I prefer option 1 with naming these. I like to name them as epoxides, but I'll take either one. Okay, so let's talk about how to prepare epoxides. And then we'll actually start using them and doing ring openings with them next time. When it comes to forming epoxides, there's 2 major ways to do that. We've already looked at one of those, and that is using a peroxy acid. So the most common form of peroxy acid is known as MCPBA. So that stands for metachloropurbenzoic acid. So this is a perbenzoic acid or peroxy acid. All of those things are the same thing. So if you see reactions written out with one versus the other, they're all the same. The cool thing that we haven't discussed yet is if you have a trans alkene, you get a retention of configuration, because remember, the way that epoxide comes in is from one side, and then basically brings in a hydrogen or an oxygen, and it just sort of, connects and back down. So it doesn't disturb where the location of the CH3s are, or the R groups, whatever the R groups are, in relationship to one another. Okay, so you can get this, but you also get the enantiomer, which I didn't draw in there earlier. So you get both enantiomers if that's something that, is an actual thing. And in the same way, if you have a cis alkene, or one that is, more complex than that, you're again going to get a retention of configuration. And again, you can end up getting the enantiomer here as well if that applies. Now, the other way to make an epoxide is through what's known as a halohydrin. These also retain their configuration. I didn't put that in here in more detail with the mechanism, just to make things a little bit more clear for you here. But let's say we're going to start with an alkene. So in other words, you have to start with an alkene in any way to get to an epoxide. You know that Br2 and H2O, when those form, these are anti to one another, right? So you form a bromonium ion, and then the OH comes in from the other direction. So these are anti to one another. Actually, they're anti-periplanar for that matter. And then we have an OH base that comes in. You do need to use a strong base there, and that's how we get our epoxides. If you were to start with a cis alkene, you would again get a cis epoxide. So here's the mechanism of the second step, because this we already looked at in Oracle 1. So what's happening on the second step is that the OH that you introduce comes and removes that hydrogen, and then the remaining oxygen kicks out that bromine. Okay, so it can internally have a rearrangement, giving you this. Okay, so you get an SN2 type of attack there, and that's how we end up making an epoxide in a different way.